This is about orbits, and while I explain orbits, I will also talk about the law of gravitation and apply Newton's laws as well. So here we have the Sun and the Earth. The Earth has a certain velocity, in fact 20 miles per second or 70,000 miles per hour. It has also an acceleration towards the Sun. That acceleration is relatively small, actually 0.006 meters per second squared, if you want to compare that to the 9.8 meters per second square of gravity here on Earth. But it is caused by the gravitational attraction by the Sun on the Earth. In turn, the Earth also attracts the Sun, and I show this in just a moment. First, this is how we get an orbit due to the attraction of the Sun on the Earth, and for simplicity I will keep the Sun fixed here, but just to show that the Earth in turn attracts the Sun, here we have, as you can see, the Sun is also kind of a little bit orbiting, being attracted by the Earth. So that's Newton's third law as well. Respectively, the law of gravitation is also what it says, that the two attract each other. But as I said, for simplicity, we just keep the Sun fixed, so that we just have the Earth going around it. The Earth would just move on with at 20 miles per second because of its inertia. What happens if the Earth wouldn't have any velocity? Well, in that case, all it would notice is a gravitational attraction by the Sun, and it would fall towards the Sun. Here again, and I also can turn on or take the anchor away from the Sun, and the two attract each other. And I guess you don't see the Sun actually moving at all because it has such a large mass. Here comes into play, I'm gonna pause this here for a moment. Here comes into play that the Earth recognizes the same gravitational attraction towards the Sun as the Sun is attracted towards the Earth. That's the law of gravitation as well as Newton's third law. As far as the acceleration is concerned, here Newton's second law comes into place. With the Earth's much smaller mass, it has a much larger acceleration. With the Sun's much more mass, it has a much less acceleration. And therefore, in this animation, we don't see it moving at all. Back towards keeping the Sun fixed here, and the Earth moving because of its inertia. It has this velocity, and it's being attracted to the Sun, so the Earth wants to move up, but it's attracted towards the Sun, so it moves a little bit left, but then it moves to the upper left, and it's being attracted to the Sun, and then moves to the upper left, and it's being attracted to the Sun. So we basically are going to get the following. Moving up, but is accelerated to the left, upper left, 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 and down, and this is a little bit too fast for me here, so I'm going to stop this here. So here it moves up, but it's attracted towards the left. Now it moves to the upper left, but attracted towards the lower left, always towards the Sun. Now it's moving to the left, but it's attracted down. Now it's moving to the lower left, but it's attracted down to the it's moving down, but it's attracted to the lower right, and so on. So those two things combined, the planet's inertia and the attraction towards the Sun that make the orbit. Wanting to move in a straight line, inertia, being attracted towards the Sun, the gravitation, that those two combined make the orbit. We can also see that because of that, the Earth is moving in a almost circular orbit actually here, maybe slightly ellipse. Notice that the Sun is not at exactly the center, obviously, but if you look casually at this here, you probably cannot distinguish this orbit, this kind of elliptical orbit, from a circle actually. We just see that the Sun is sitting in one of the two foci, not the center of it. Lastly, I changed our system here a little bit. I made the orbiting object here much slower. And so, for example, we have a moon around a planet like Nereid around Neptune. And because it's slower when it orbits, it actually is a quite elliptical orbit. As we saw earlier, the Earth's orbit is so ever slightly elliptical that we cannot distinguish it from a circle. But for this one here, so same things apply. Because of its inertia, it wants to go forward, and because of gravitation, it's pulled into this orbit. We can also see easily Kepler's first law. It's an ellipse. We can see Kepler's second law, that it orbits really fast when it's close and slow when it's farther away, respectively. Starting over again, when we put the acceleration in here, we can see that when it's really close, the acceleration is huge, because gravitational law says that because of the distance we get a larger force, and then Newton's second law, we calculate the acceleration and we get a huge acceleration. That's why you see these overproportional acceleration vectors. Here we have a system of two masses in orbit that are closer in mass. For example, Pluto and its moon Charon. And as we can see, now this time I didn't fix the central object because the masses are closer, so their accelerations are closer as well, and the central object actually does move, so you can easily see Newton's third law at work. The two are orbiting each other. This view includes the common center of mass. Notice that it stays the same as the two orbit each other. The same would apply to, for example, the Earth and Moon system, but the center of mass would be much closer to the Earth, because the Earth has a much smaller acceleration due to its much larger mass than that one of the Moon. Again, this all ties in with Newton's third law, Newton's second law. So here we have Earth and Mars orbiting the Sun, and because the Earth is closer to the Sun, it has a larger gravitational force, larger acceleration, and so that overall, and because of its larger speed as well, produces a faster orbit than Mars' orbit does. We can also again see that both of these are ellipses, and if I start over again, then we can nicely see that, of course, the Earth is moving much faster around the Sun due to Kepler's, or which illustrates Kepler's third law.